This is our season 4, episode 4, and we're studying properties of logarithms. Yeah, pretty awesome. This is our warm up. We've begun a little bit without you at home, if you're viewing at home. This is 3 to the 12th, and we have 3 to the 4th, and you can subtract these exponents. This is like saying 3 times 3 times 3 times 3 times 3 times 3, and it goes 12 times. And then over here we got 3 times 3 times 3 times 3, and these cancel. They annihilate each other. And this, whoop, I went too many. 1, 2, 3, 4, and then the rest would be how many? 8. There'd be 8. There'd be 8 left over. But this canceling, they don't go away so much as they equal 1. 3 divided by 3 is 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 1. And then you leave it as 1 times whatever remains. It's fancy counting. Yeah. This is 4 to the 3rd, and this is 4 to the negative 1. If you want to rewrite this as 4 to the 3rd times 4 to the 1, you could do that because the negative 1, you could bring it up into the numerator. What will be on the denominator? Just a 1. So what is it going to be? You could say either 3 minus negative 1. 3 minus negative 1 is 4. Or you could say it as 3 plus a positive 1, which is 4. And what do you do in this situation? Yeah, here we multiply. Okay? This is 7 to the 3rd times 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 what? 7 to the 3rd. And now this is 3, 3, 3, 3, and 3. This is going to be 7 to the 15th power. But this is repeated multiplication. And we got, if we raise a power to a power, we multiply those. Right? So if I had, for example, I'll give you one other one, something to think about. If I have x to the 5th to the 2nd power, what does that equal? X to the 10th. You can multiply these, because this x to the 5th times x to the 5th. When you add those exponents, you get x to the 10th. Question? I thought I heard you say wait.
No, like that was understanding the flow in my brain.
Okay. Wait is used in many different contexts these days. This is log base x of x equals 1. How do you rewrite this as an exponential form? Remember I did this little recycle sign? This is from all the way back from yesterday. This is pretty long time ago. This is x to the 1 equals x, yeah? X to the 1 equals 1, x. And then this one we got x to the 0 power equals 1. Remember this power is always your exponent. Right? So we get x to the 0 power equals 1. Question?
Is 0 to the 0 still 1?
That's a great question.
I think it
yeah.
is.
Well, but how? There's just like.
Well, this is something that I've spent a little bit of time looking at, but hard to explain in a short amount of time. But one thing that's kind of neat about the internet is you can Google it, 0 to the 0 power, but not right now because we got this lesson.
No, but it's a rule that has to be always.
Well, math has some tricky things, like 1 to the infinity power when you're doing limits is not 1. That's interesting, isn't it?
How?
Yeah, it's bizarre, crazy, but you got to take calculus to find out. I don't want to.
How would that work? 'Cause no matter how many times you multiply it times.
Yeah, 1 times 1 times 1, but things are weird at infinity, that's the thing.
But
Things get kind of weird.
infinity is still every number, so like.
Infinity's not every number, it's a very large. It's not actually a number.
Infinity is.
It's the concept of all existing
Yeah.
numbers.
No, it's not all existing numbers. Why do you keep saying that? It's large, it's very, very large. You don't put all numbers together somehow.
No. It's just every number.
No.
That's how you know.
It's not, infinity is not 1. If infinity is every number, then you say infinity is 1 and infinity is 2 and infinity.
It's like if you look at a graph, like it would scale up to the degree.
We'll talk about it later. We'll talk about
It
that.
would increase by 1.
Let's learn our lesson
Yeah, let's-
today.
Let's continue. That's fascinating. I would like to talk about this more in the future, but not right now. Right. Logarithms are exponents, so you can derive the properties of logarithms. Now there are 3 properties I want you to come away with understanding. Okay, there's 3. So if you at the end of this lesson you understand 3 properties of logs, then I have succeeded in showing you some things. But this is a log. What's the base of this log? Log base what?
10.
10. Why? How do you know?
Because there's not one.
There's not a number written, so it's log base 10. Okay, we learned that yesterday. So this is log base 10 of j, this is log base 10 of a, this is log base 10 of m, and this is equals log m. Okay, and why is that? Well, when you're multiplying two numbers with the same base, we can add the exponents, can't we? And what did I say yesterday? Each one of these logs is an exponent. So if I'm doing exponent here, exponent here, exponent here, then what it was all three together. It was multiplication. So we multiply these bases, then we can add the exponents. And so this is addition of exponents.
Would it be 30 or no? Because each of it's 10.
We don't mess with the base. Yeah, don't change the base. Just like we don't mess with the base here, right? This is base stays the same. Okay? Just like we don't mess with the base on the logs. All right? So here we go. We do not add the bases. Here is the property. If we have a log with the same base, it's got to have the same base, and we have an addition going on, the addition of two logs, we can write it, we can what they can call condense into one log. The log is going to have that base, log base 6, and we can multiply these and make 36. What's 9 times 4? 36. Okay? So if we have two separate logs that have the same base, we can put them into one log. Okay, that's the first thing I want you to understand is if you have two separate logs with the same base, we can put them into one log. And if we had one log with a multiplication going on, we can separate it into two. We can actually expand it or condense it, whichever way you want to go. Yes?
Why would we multiply it and not add it?
Well, it's just like I said up here. If we have the exponents are being added, then it was a multiplication of two things. So multiplying here, you add the exponents. Right? So that's the connection because we're talking about exponents. This is an exponent, this is an exponent, this is an exponent. So adding the exponents when we're multiplying.
And
Right?
Opposite.
Wait.
Yeah.
It's 4 and 9.
No, 4 and 9 are the what is. What is it? For example, let's rewrite this. 6 to what power equals 4? Right? 6 to what power equals 4? That's how you'd write that one. And then 6 to what power equals 9? Right? So if I were going to add these together, the exponents, these exponents are adding, then these must have been multiplying. If we're going to add these exponents, then we must be multiplying these things. It's kind of hard to see that connection, but you need to absolutely remember the property. The property is, if we have addition of logs, then we multiply these two things what you're logging. Right? Now, couldn't you solve this a lot easier now? Because we don't know log base 6 of 4 and log base 6 of 9. But couldn't we solve a log base 6 of 36? Say it out loud. 2. How do you know that?
Because 6 to the power of 2.
Exactly. 6 to the power 2 equals 36. So we can get this answer a lot easier than if we were trying to do them separately. And that's the point. If we were trying to do them separately, it would be very difficult. What's log base 6 of 4? I don't know. What's log base 6 of 9? Not sure. But I know log base 6 of 36 too. That I do know. Because 6 to the power 2 is 36. Question? Well, let's try another one. See what happens. Okay? This one says log base 5 of 5, and then it says plus log base 5 of 25. Now, each one of these individually, I know this is going to be 1 and this is going to be 2. Right? Because 5 to the second equals 25. 5 to the first equals 5. 1 and 2. I know this is going to be 3. The answer is going to be 3. Hopefully we can all agree. But let's write it as one log. We can say log base 5, and what do we do with these numbers? What do we do with this and this? Multiply them. What's 5 times 25? 125. And then you say to yourself, well, 5 to what power is 125? That's 3. And so we get the same answer either way. Question? How am I getting 3? I'm saying this in my head. I'm saying 5 to what power? This is a question mark. Equals 125. And I know 5 times 5 is 25, and another 5 is 125, so that's 3. All right, and look here, you can actually write it, let's try one more. Express as a single logarithm, simplify if possible. So log base 1/3. Log base 1/3 of what? 3. How'd you get that?
27 by 9.
Yeah, 27 and 1/9, right? 27 times 1/9, or 27 divided by 9 equals 3. So this is log base 1/3 of 3. And what do you think? How can we get an answer for this? 1/3 to what power equals 3? Don't yell it out loud. Just hold it for a second because I want everyone to at least think of an answer. 1/3 to some power equals 3. Don't yell it out. Good morning. How are you? Make sure.
Why did you do it? Oh, okay.
All right. So who can help me with this answer? Who? Raise your hand. Don't just yell it out. You already answered one, young lady. But if you're the only one, I'll call it. Ramon.
Is it 9?
9, not 9. Nope. If I raise 1/3 to the 9th power, that's 1/3 times 1/3 times 1/3 times 1/3 times 1/3. You know what I'm saying? So this is 1/3 to what power? Not 9.
Oh, wait, I think I got it.
1/3 to some power equals 3. All right, go ahead, DJ.
-1.
-1. Nailed it. That's right. -1. Because what does a negative power do? It switches it from the top to the bottom or the bottom to the top, right? So 1/3 to the -1 power equals 3. This power stuff is not easy. I would not say that by any stretch of the imagination, but it's fun. Well, I wouldn't say it's fun. I would say it's toast terrific.
It's
What's your?
I would say on a level of on a scale, I'd say the level of awesome of this particular lesson is probably like a 3.
Out of?
17 million.
Yeah, not that all.
that's not
why-
what
Man, I mean it is math, bro.
Could be worse.
Yeah, it could be a 2.
Yes,
What's the exact definition of toast
just terrific.
All I know is the students say it all the time, so I'm just trying to pick up what you guys are laying down. I'm just smelling what you're stepping in now.
How the you pick it up in the lane.
That's right.
How your calculus kids?
How are the calculus kids? What?
Did you pick it up in the calculus?
No, it's a 10th grader mostly.
Or it's the analytical thinking kid.
No.
Or your student.
When I say it in my analytical thinking class, they kind of just look at me like, what?
That's what we do.
No, we're
No,
like,
the 10th graders are right in with it.
totally
They're like,
gets
what?
us.
Yeah. See?
It just makes
No.
sense. Allie, if you don't like him, sleep.
Okay, here we go. We're gonna move on.
Set this damn
It turns out that when we're dividing and they have the same base, we did this in a warm-up. If we divide two things that have the same base, we can subtract the exponents. M minus n. Okay? That is a true statement because we did that in the warm-up, right? If I have, x to the 10th divided by x to the 3rd, I would get x to the 7th. Yeah, we're good. So now, it turns out that we can also do this with logs. If we're subtracting logs, we can actually divide these numbers. Okay, so we're working backwards. So when we had division, we subtracted the exponents. When we're subtracting the exponents, we can consider this division.
But you can only do it if the base is
Exactly. See how I got 8 to the 5th and b to the 3rd? That means nothing as far as, there's no simplifying you can do there. So they have to be the same base. Just, that's a caution. And if you notice that this caution has an exclamation point, it's actually 3 exclamation points and 1 factorial sign. That's interesting how they did that. We'll have to talk about that later. All right, subtracting logarithms. So if we have subtraction here, this is log base 5 of 100 minus log base 5 of 4. So this is going to be log base 5, and we can divide these things. We can divide the 100 and the 4, and that's going to give us what? 25. And we know this. 5 to what power equals 25? 5 to the second power equals 25. And once again, I will say, 5 to what power is 100? Not sure. 5 to what power is 4? Really don't know. But in this case, 5 to what power is 25? 2, that's easy. So sometimes condensing these logs is going to make your life a lot easier to figure out the answer.
Wait, how did you get
So we can divide the 100 and the 4. What you're taking the log of can be divided when your logs are being subtracted. Okay, let's try another one. Log. Actually, you write this one down, and then I'll give you about 30 to 45 seconds and see if you guys can get the right answer. Try that one. It's right there. turn to your neighbor and just show them your answer and just say, hey, what'd you get? Maybe sometimes you gotta say it more than once. If the person doesn't respond, maybe ask again.
What'd you get? What'd you get?
Oh my god, log 7.
I got log 7.
Wait, how do you?
Don't say log 7, log base 7.
I got
Oh,
log
log
7.
base.
7.
No, log base 7.
Wait, what do you say? And then how do you say the next thing?
Of,
Of 7.
yep, log base 7 of 7.
Log base 7 of 7
Equals 1.
Equals 1. Nice job, everyone. I heard it from at least 3 people, and that's terrific. Hey, give yourself a round of applause. What I'll do is I'll put my hands next to the microphone so it sounds like really loud. That's really loud. I can't hear anything. Okay, good. You guys did a great job. All right. Now it turns out that when you see subtraction, what you can do is you can divide the things you're taking along. That's the bottom line. So there's 2 properties I shared with you already. Okay, 2 properties, and I'll do a recap at the end. How's that sound?
Okay.
All right. This is the third and final property is. You remember that when I have a power raised to a power, 3 to the 5th squared, what does that equal? 3 to the... This is 3 to the 10th because it's a power raised to a power. 3 to the 5th squared is 3 to the 5th times 3 to the 5th. That's 3 to the 10th if you're thinking about how you could add those. The point is this. If you have a power raised to a power, then there's multiplication, right? So if you're working it backwards, see how this log is 10 to the 3rd, then I could take log base 10 and just multiply it by 3. That's too loud. Right? So this is log of 10 times 10 times 10, or log of 10, log of 10, log of 10, or 3 times the log of 10. So what you can do, what you're allowed to do with logs, and this is really quite fantastic that we're learning this because it's so important. This 6 here is on the power of 32, the power of 32 to the power of 6. I can actually move this 6 out and just make it 6 times log base 2 of 32. This power here,
With no parentheses.
if you want to put parentheses, you could. You could put it here around this or around the 32. Right now it doesn't need parentheses. This would be readable. So long as your 2 is definitely a subscript. Now, let me ask you this. 6, what is log base 2 of 32? What is log base 2 of 32? Think about that for a minute.
5.
That's right. And 2 to the 5th power is 32. I think I asked you guys yesterday, I said 2 to what power is 32, and someone said 5, right? So this is 5. This whole entire thing equals 5. And so what is 6 times 5? 30. Okay, let's try another one.
Whoa.
Go ahead.
Why were you trying to get 30?
I wasn't trying to get 30, that just was the answer. That's like saying I'm not trying to be 39, it's just my age.
Explain what you just did. 6 times 5.
This is 6. We agree that we can bring the 6 out because that's the new property I just shared with you.
Okay, yeah.
Okay. Log base 2 of 32. Well, 2 to what power is 32? 2 to some power equals 32. And 2 to the 5th power is 32. So this entire thing equals 5. So 6 times 5 is 30.
Okay.
Okay, good morning, Daniel. Look here now. We got this one. We can bring this 20 out here. And we can call this 20 times the log base 4 of 4. This property says if your power is on the 4 only. Okay? I want to just stress something that's not true. If I have the log base 10 of 3, and I raise the whole thing to the second, in this case I cannot bring this 2 out. The 2 has to be only on what you're taking the log of. If this 2 were to come out, that would be false. This is not 2 times the log of 3. That's not correct. This 2 has to be only on what you're taking the log of. So this 20 is on this 4. So the 20 can come out and multiply 20 times log base 4 of 4. Now what is the log base 4 of 4?
1.
Very good. So it's going to be 20 times 1.
Do we still use the what's it called? When there's no base, you do 2.
Yep, always. For the rest of your lives. That's a mathematical standard. If there's no base, it's log base 10. In fact, we're going to learn in the, not next section, but the section after that, we're going to learn about base E, which is very interesting as well. All right, so can you take some time, express this as a product, and then simplify if you know how to do it. So try these three on your works. Get set. And welcome back. So during our break, we had time to solve these.
Wait, can I do this?
I'm just going to do this because I'm going to go quickly. And many of the people in class have already done the problem. So this would be, you bring the 4 out front. Because the exponent is on the 10, you can bring the 4 out front. So it's 4 times the log of 10. Well, log, this is base 10. Log base 10 of 10 is 1. In fact, if this base matches the number you're taking log of, it's always 1. Right? Hopefully that makes some sense to you. If it's log base 2 of 2, that'd be 1. If it's log base 5 of 5, that'd be 1. It will always be 1 if that matches the base. So this would be 4 times 1 equals 4. This one here, we can bring the 2 out. This is 2 times the log base 5 of 25. And we know that log base 5 of 25 is 2 because 5 to the second is 25. So this is 2 times 2. And that gives you 4. And this one, 2 to what power? Well, we bring the 5 out. Start there. Then we get log base 2 of 1/2. Taking the log of 1/2 is base 2. And when I say 2 to what power is 1/2, most of you came up with this, which was just excellent, just terrific. 2 to the -1 is 1/2. So this is 5. This is 5 times -1. And that equals -5. All right, are there any follow-up questions on this part? All right, let's try, flip to the next page. Try a few more of these. So just a little bit, inverse properties of logarithms and exponents. So they undo each other, right? So logs undo each other. Logs and exponents, they undo each other. So if I have something like this, 3, log base 3 of 3 to the 11th. Well, we already said log base 3 of 3 is 1. So if we bring our 11 out, this would just be 11. They're canceling each other. They're canceling each other. So log base 3 of 3 to the 11th is 11. Because the log base 3 of 3, they cancel and make a 1. So you see this is 3 to the 11th, and then we do a log base 3 of it. They're undoing each other, and you get 11 back.
Is that only because they're the same number?
Yeah, they got to be the same number. So 3 to the 11th, say we have a function that's 3 to the 11th, or 3 to the x. And then we take the log base 3 of it. Log base 3 of this function 3 to the 11th. These undo each other, and you get 11. The log base 3 and 3 to the x, these are inverse functions. So log base 3 of x and 3 to the x, those are inverse. They cancel each other out. You get 11. You put 11 in, you get 11 out. Okay? Let me give you another example. This one, we can rewrite this. I know 81 is 3 to the 4th. Maybe you don't know that. That's fine. But I know it. So I know this is log base 3 of 3 to the 4th. And log base 3 of 3 to the 4th is 4. They cancel each other.
3 to the 4th
Yep. So maybe you didn't recognize that 3 to the 4th is 81, so this problem would be a little bit more challenging. But one other way you could do this is say, you know, what can I multiply? What multiplies 81? What are some very common multiples of factors of 81? 9. Okay, let's think about it this way. We got log base 3 of 9 plus log base 3 of 9. Couldn't we do this based on our earlier property that 9 times 9 is 81, so we can separate it into 2 logs? And what's log base 3 of 9? 2. And what's log base 3 of 9? And 2 plus 2 makes 4. So you can break it down that way too. You can use your log properties to look at it a different way and say, well, this is 81. I know that's 9 times 9. Or 27 times 3. Okay, this one is 5 to the log base. That's supposed to be written like this. 5 to the log base 5 of 10. You know what they do? They undo each other. 5 to the log base 5, whatever's in there is going to be my answer. Because they're inverse operations. So the answer is going to be 10. These undo each other. 5 to the x, and then log base 5 of x. If you put one into the other, you always get what you started with. That's my point. If I put a 10 in here, and I take and get the answer, and then put that in there, I'm going to get 10 back. They undo each other. So what do you get for A? Try these.
0.
Yeah, 0.9. Yeah, 0.9. Because this log base 10 of 10, it cancels. And then how about this one? It says 2 to the log base 2 of 8x.
8x.
8x. Again, they're inverse operations. They cancel each other.
So it's just the exponent.
Yeah, so it's basically just the exponent.
Yeah, because these cancel each other. Log base 10 of 10 is 1. They cancel each other, so we just get the exponent. They're inverse operations.
Hell no.
This is an outdated lesson. It says most calculators calculate logarithms only in base 10 or natural log. But that's not true anymore. Your calculators, all of our calculators we have in the classroom, they can do that log base. You can hit math and you go to log base and it does it for you. Okay, we did it. We can do this in our calculator. Okay, we can do log base 32 of 8. But it used to be that you couldn't do that, so they had to show. This is still true. Change your base formula, but it's not as relevant as it used to be. Let's just say that. Okay. So what it is that we can change to any base we want, and we take the log of the top and log of the bottom. So what would be a good base to change this to? If we have a 32 and an 8, what might be a good base? Like what number can you think of that is an exponent? Can go into 32 and 8.
4.
I'm thinking 2. Someone said 2. 4 is not true because 4 to what power is 8? 4 to what power is 32?
Oh.
Right, but 2.
3.
3 doesn't go into 8.
Because 16 times 4.
So the idea is even if you just sort of know that it would be 2, like it's just like a thought you have, then try it and see what happens. Okay? It doesn't mean you definitely know it for sure, but check this out. I can do this formula where the log base 32 of 8 can be rewritten as a log base 2 of 8 divided by the log base 2 of 32. Okay, I'm allowed to do this because this is called a change in base formula. So all I'm doing is I'm taking the one that's in effect higher on the page. This 8 is a little bit higher than 32. I put that on top. The 32 is a little bit lower. I put that on the bottom. I can change it to any base I want. I can change it to log base 10, log base 50, log base 100. I can change it to any base I want. I chose 2 because I know that 2 to some power is going to be 8 and 2 to some power is going to be 32. And so check this out. What is 2 to what power is 8? 3. 2 times 2 times 2. That's 8. And 2 to what power is 32? 5. So we got our answer is 3/5. Okay? So it used to be that because the calculator, now I don't have my calculator open, I can open it. Just give it a few seconds to warm up. Your calculators come on a little quicker than mine. But it used to be that you can use log base 10 in your calculator. So you do something like this. If I had a problem, log base 32 of 8, I would do log of 8 divided by log of 10, log of 32. And then I give my answer 0.6 or 3/5. Okay? So it would just be because the calculator couldn't do a different base, you would have to use log base 10. So you do log of 8 divided by log of 32. In this case, we use log base 2 of 8 and log base 2 of 32, so we get the answer. But now our calculators do math. You go up to log base, and you say log base 32 of 8, and you get the answer 0.6 or 3/5.
That's cool.
Okay, your calculator has this. If you have a calculator that is not updated, right? You hit math and you go up and you don't see log base, come see me. I can update it, and so you can get that functionality. All mine are updated, but if you have your own and it's not, then let me know.
How do you go?
You got to plug into a calculator that's already been updated and transfer the operating system. It's not hard. It just takes about 5 minutes. Okay, so it says evaluate these. Notice I got a 9 and a 27. I'm thinking 3. If I change this to log base 3, I think this would be helpful. Let's try it. See what happens. Because I know 3 goes into 9 as an exponent and 3 goes into 27 as an exponent. So we say log base 3 of something and log base 3 of something else. So which one goes on top, which one goes on the bottom? What's that?
27.
27 goes on the top and 9 on the bottom. So we say 27 up here, log base 3 of 27. So we say 9 down here. I chose base 3 because I see 9 and 27. I'm thinking 3 is going to go into both of those.
Wait,
Wait.
did you choose 27 to go on top because it's farther?
You just the way I remember it, and you don't have to remember this exactly, but I see it higher on the page, and I remember it goes on top. See, the 9 is a subscript, so I remember it goes on the bottom.
Where'd you?
Which one do you want to know? Where I got the 3?
I want to know. Yeah. Where'd you?
The 3, because I see 9 and I see 27, I think 3 is going to work, right? 3 is going to go into 9 with an exponent, and 3 is going to go into 27 with an exponent.
What if 3 doesn't work?
Let's try something else. But 3 to the what is 27? Anybody?
Three.
Third, and 3 to the what is 9?
Two.
You get 3 over 2. This is where math gets interesting and fun.
No, just interesting.
Oh, I got 8 and 16.
4.
4 is not a.
Two.
How about 2? Yeah,
You
2.
gotta upload this video.
Even if you do get
Oh, definitely.
Like,
So,
toast
log base 2 of 16 on top, and log base 2, we can change it to any base we want, but I'm choosing 2 because I know that 2 to some power is 16 and 2 to some power is 8. That's why I'm choosing 2. So 2 to what power is 16? 2 to what power is 8?
5.
Three.
Oh.
So 4/3. Or 1.3 would be. Okay, some practice problems on the bottom there. This is 2 to what power is 8 to the 10,000? This is kind of tricky. So let me show you how I can make this a little bit better. Okay.
Will be just 10,000.
No, it's gonna be 10,000. If this were a 2, that'd be 10,000. But it's
So
not.
at 2, you can do that. 'Cause 2 to the 3rd. And
Yep.
so it'll be 3.
You're getting there. You're very close. Check this out. I'm gonna write this as there's multiple ways to do this, but I'm gonna take this 10,000 out. I'm gonna say this is 10,000 times log base 2 of 8.
So that'll be 34.
That's right.
So, okay.
322 million.
So this one's gonna be 2 to what power is 8? Anybody?
3.
3. So we do 10,000 times 3.
Oh.
30,000. Okay. So I'm allowed to, because of the property that I learned a few minutes ago, is I learned that I can bring this 10,000 out to the front and be multiplication. And we know 2 to what power is 8 is 3. Say it again. I'm sorry, one more time. Who's talking?
Where are you getting the 3?
Where am I getting the 3 from? 2 to what power is 8? That's where the 3 comes from. 2 to some power equals 8. And that is 3. That's 2 to the 3rd power is 8. So knowing your powers is going to be very helpful, obviously.
X minus 1.
X minus 1. Because these are the same base. 4 log base 4 of 4 to the x minus 1 is just x minus 1. This is the reason we're solving these, try to bring those exponents down to a usable level. Oh, look out, we got 10 to the log base 10 of 125.
Oh, because there's no base. So it's just 10, so that means it's 125.
That's right. Yep, there's no base, then it's log base 10. And then this one is 6. Oh, look out, we got a tough one here.
It's
Find
that one.
something.
Isn't it just that? You gotta do that.
You could do this stuff, change your base. Can you think of a good base to change it to?
4.
8.
I changed it to 4.
8 definitely goes into 64, but 8 to the 3rd is not 128.
About 4.
I changed it to
Does 4 go into 128? If you have 4 to some powers, that gives you 128.
Probably.
Yeah, 4.
Unfortunately, it doesn't. 4 goes like this.
Oh.
4, 16, 64, and all the way up to 256. Yeah, too high. How about 2?
I said 5.
Let's try 2 and see what happens. We do log. Let's try it. Log base 2 of 128 and log base 2 of 64. Now, I know 64, I know that's going to be 6 on the bottom. Because 32 is 5. Right? 2 to the 5th is 32. 2 to the 6th.
76.
Yep. And then one more higher is 128. 76. Interesting stuff. Very, very interesting.
Cool. We're done with the notes.
All right.
Really